So it's a pleasure to introduce an old friend of mine, Phillippe Robert from INRIA Rocquencourt and the École Polytechnique, and he will speak about the evolution of the spatial stochastic network.
Okay, thank you, Ono. I would like to thank Kavita and Takis for the invitation and Sergei for the invitation to the program. So I'm very glad to be here. It's a very nice place for research. Okay, so today I will talk about spatial networks. So I could put it differently. I would say it's a simple problem with a simple solution. I would try to convince you. You will see it's not difficult to realize that. Okay, so introduction. So what kind of things I will be looking at? There will be the following thing that I'm in some space. I have points, which I will call plus particles. And my state is the locations of these particles in my state space. Okay? So, of course, it doesn't stay like that forever. And there are some dynamic. And dynamic can be of different type, arrivals, like this one. And if it's a plus particle, then it stays where it arrives. And I have a new particle in my system. Okay? Most interesting is when I have a minus particle. So there will be a blue. A minus particle, as you may expect, will kill a plus particle. Otherwise, it will not deserve its name. Okay? And but here, and this is where you will have interaction. Interaction is as follows, that you have a small neighborhood around the location of the particle, and if there is nobody around, then it does nothing. Okay? So it's lost. Nothing. So the minus particles didn't have any impact on the network as long as I have nobody in this domain. Okay? Situation is different, so state isn't changed. Situation is different if in the neighborhood there are pluses. Okay? So this is where you have to define a policy just to say which particle you will kill, because of course you don't kill everybody. It could be, but let's say it's a nice movie. You only kill one. And a possible policy is just to kill the closest. So this is which I will call the greedy. Greedy policy, I kill the closest in my neighborhood. Bang. And it's dead, and my minus particle disappears. Okay? So this is how it works. So this is what I will call local greedy policy. Another possibility is just to kill a plus at random. So take a plus at random, I kill it, and same thing, I disappear. Okay? So this is what I will call local random policy. Okay? So the interaction the particles just because of their location with respect to each other. Okay? So with a random policy, if you have many particles which are grouped together, then you are more likely to survive than if you are alone in the desert, let's say. Okay. So the general framework is as follows. You assume that you have arrival rate of pluses and minus, and that their locations have some distribution on some metric space H. And I will consider only two policies here, greedy or random, but there are others that we will talk about. And simple problem is I'm looking at total number of pluses. And I'm assuming that there are much more minus arriving than pluses. Does it converge to a finite equilibrium? In other words, does the total number of pluses remain converges in distribution as long as this condition is satisfied? Okay, so this is a simple simple model, as I promised. Okay, so some motivations. So there are various. So the plus may represent request for bandwidth in a network, and the minus in some way represent the bandwidth which is provided locally. And of course, in another context when the plus are mobile, then with the mobility, you could expect to catch some bandwidth around. But here, we are just they are just trapped, so they have to wait to have some capacity around. Okay, so I will come back to this on this point. And I must say, okay, so the same question, and this comes from, in fact, from a paper by Sergey, and I'm very grateful to him for introducing me to this problem. So he wrote a paper for the Erlang conference in the other sequence of open problems, and this was an open problem mentioned by Sergey for the one-dimensional torus. So this was the most simple example, the simplest example he had, and this is at the origin of this talk. And by the way, I should thank him again also, just because afterwards I realized that one of my old paper, the first paper I wrote for a mathematical journal, I used a trick that I could use perhaps in this situation. So I will come back to that. So it makes me younger at some point.
One-dimensional torus also called a circle.
Yes, yes. So you will see I'm not consistent, because sometimes I will use torus circle. Just I'm not very strict on that, as you will see.
I was told by Venkat about.
Yes, and Venkat, and so we exchanged with Venkat, with Richard Serfozo, with.
I think Nick Serfozo is the origin of this problem.
Yeah. So I had the contact with all the people, and Volker at some point also on this problem. Yeah, so I'm very grateful for the exchanges I had at that time. Okay, so another motivation, and this is where, which is related to the work I did a long time ago, in fact, 87. I was interested at that time by online matching problems. And so the problem is the following. You have to pack items. You have items of size xn in 0, 1. And you want to pack them in bins of size 1. And you are not very optimistic. You think that at most you will put 2 in each bin, and then you don't worry about using a complicated algorithm just to keep track of all the states that you have. And so the algorithm, it was an algorithm designed by Karp and others, worked as follows. So my items, if I have an item of size x, if x is less than half, then I put a point at 1 minus x. So I will be in the state space 1/2, 1. But if it's a minus, then my location will be x. And this works as follows. So if I have a minus, and if it finds a plus on its right, it means that if x is less than 1 minus x prime, then x and x prime can be put in the same bin. So I can pack them, and then I kill the plus. So this is a way of fixing it. In the other case, if a minus does not find a plus on its right, then I give up. It will be alone in the bin. And this is how it works. Okay, so this is a paper by Karp in '84, and this is the paper I studied, the algorithm I studied at that time. Okay. Marginal. It's also a marginal motivation. You would like to study birth and death processes on a continuous state space. Okay. And it differs from the classical framework that we know when we have a discrete state space. So I will come back to this point, and where you can use some classical tools of Markov chains. Okay. Continuous setting, in fact, complicates a little the analysis. I guess this is one of the main difficulties in this area. But I will try to convince you that if you put the things properly, then you don't care about continuous state space or whatsoever. Okay, and also, and not only because you have annoying technicalities that you have to deal with. Okay, well, as you have sometimes with continuous state space Markov chains, where you have annoying details you have to go through. Okay, so this is, let's say, the framework. So if I look at the literature, there are some activity in these special birth and death processes. So Volker and his colleagues worked on some models of, for the growth of proteins in a series of papers where they are studying more birth processes. Pablo studied also a simulation of birth processes with some specific death rate, if I'm not mistaken, where here the result was concerning simulation procedure. And Garcia and Kurtz also studied birth and death processes, but in that case the death rate was constant and birth rate was depending on the state space, quite general by the way, and more important, it was a non-compact state space, which makes a difference in this case. Okay, so general model of configuration is just you have a set of points and it evolves according, so in a Markovian setting, you may have a birth at rate x given the configuration xi, and or death rate or birth rate because of x belonging to the configuration at y, and so on. So you can imagine that you have all these Markov processes. So there has been quite some activity in this domain recently. And there is a quite good paper by Penrose where there is a survey of these models where it describes what's going on. Let's say, and the literature is mostly devoted to the existence result. And when you don't have a compact state space, the existence is a little more tricky because because of the local interaction, and you have infinitely many exponential flux, then you may have some trouble. So this is reminiscent of what was going on in interacting particle systems where on 0, 1 the power z, where you have to be careful to define your system. So this is a kind of generalization of that. And the results which are mentioned mostly concern spatial limit theorem. So you assume that you have some homogeneity condition, and you look at the distribution at some instant, and you look at the spatial limit or on a sphere of size n, and you look at the limit of what you can get, or lower Plot numbers and central limit theorem. There are nice results in this domain. Basically, this is an extension in some way of the work by Dawson in the late 80s, early 90s on measured value processes, where some of the processes that the previous speaker mentioned were included with hierarchical processes and so on. So this is an old tradition in some way. But there are few results concerning aseptic behavior. And this is one of the point. And it's normal in some way. You cannot expect to say something concrete about the invariant distribution if you do not specify a little what you are going to look at. So you are going to look at some specific models and just try to study them as closely as possible, like the exclusion process in interaction particle system, which has been studied a lot. But this is only a small class, but very important class. So this is the idea. Okay, so I will be more mathematical now. I've been running, but let's say I will introduce notations. So I assume that my arrival process is stationary of particles. My locations is just a stationary sequence, and as well as the types of particles. Okay, so for the moment, I don't need too much, but since I have no result, I can take the assumptions I want. There is no trouble, as somebody mentioned 2 or 3 days ago in this domain, as long as you have no theorem. But there is an important assumption that which is easy to understand, is that for all the results, most of the results, you have to assume that the location and the types are independent. Otherwise, it's easy to realize that you may be in trouble even under nice conditions. So, but that's normal. Okay. And so, I forgot to tell that I will use P plus as the probability of having a plus, and with this notation, then lambda plus is simply lambda P plus and lambda minus, and my natural condition is simply P plus less than a half. Of course, I will be only interested in P plus less than half, otherwise it's quite easy to see that you will saturate your state space, you can characterize the limit and so on, so this is not a problem at all.
But by the way, is the arrival process independent as well of the other
Hmm?
guys? Is the arrival process independent?
For the moment, yes. For the moment, yes. I don't need that. There are only one. I will tell you one place where I need independence, just to show you how it's going on. So I don't need to have independence of the because okay. I will come back to that. Okay. So I will first begin with a simple example to convince you that the discrete case is not interesting. So you assume that the locations are only on the discrete set. It can be infinite, but a discrete set. And if you look at nk, the number of plus at xk at time t, then you have a rival rate lambda p plus, and you have also a rival rate of minus lambda 1 minus p plus. Okay, so it's easy to realize that it will be certainly bounded by an MM1Q with input rate lambda p plus probability of being there, and same thing for the service rate, which is represented by the particles. Okay, so if you look at the total at your system, then it's bounded by MM1Q with service rate lambda p plus and lambda 1 minus p.
You only kill in the side.
Yes, because you don't need to move. They are just where you want.
But if there is nobody there, you can kill your neighbor.
Yeah, but this is why it's bounded. We say upper bounded. I'm sorry. So the real number will be less than MM1. Okay? This is what I meant. So, yeah. Okay, so in this case, no problem. And this is where really a continuous feature of this distribution of x1 is playing a role. It will change slightly the qualitative behavior. Okay, so how do I describe this configuration? So it's a simple way of doing that just by considering discrete distribution with a Dirac measure. So this is a Dirac measure at xk, and this is a point process on my state space H. Okay, so I have a finite sum of Dirac measures. And I will look at the embedded process. I will look at the state after the arrival of next particle. So I will just rephrase mathematically what I have said with my drawing here. Just say that if you have an arrival, I1 is plus, then you simply add Dirac measure at the location x1. Okay, so this is Z. And when you have a minus, then you have to worry if there is somebody around. So dA1 will be a ball of radius 1 centered at A. So you will kill somebody when this number, which is simply the number of points of n0 inside the ball of radius 1, if it's not 0. And in this case, you will be able to kill a plus. Okay? And you will kill some point that I will denote by T1, X1, N0, meaning that at location X1, I will kill somebody from N0, but still under the condition that this is not 0. And so I subtract this Dirac measure. Okay? Okay, and of course my T1. Yeah, this is what I'm going to explain. Very good. Good question. T1 is, of course, depends on the policy, and T1 for the greedy policy is just the points of N0, which is at the smallest distance, provided that it is at distance strictly less than 1. Okay, that's the definition I took. And of course, if there are several, you take a random variable, and that's it. Random policy, you just take a y, which is a random point, among the point of N0 within this the ball of Bx1. Okay? So if I do that, then I have some evolution equation, which says I add on the event I add, and I subtract, provided that it's a minus and that there is somebody around, and in fact I remove that. So this is my discrete dynamic of my process. Okay, so I am describing the evolution of point processes in this way. Okay, so now the question, initial question was, what is the associated behavior of this sequence when p plus is less than half? So precisely, are there limiting points? And more important, is a possible limit in the set of finite distributions, which is finite measures on h. Otherwise, in another thing, and the variable n of h is it almost surely finite. So this is the key point, of course. Okay, so so with this kind of description, then you may formulate it differently. Say, I'm looking at some distribution on the set of configuration, that is the set of point processes, such that my probability is invariant with respect to this functional. Okay, this is a way of describing equilibrium. Equilibrium, I will have, is simply a probability distribution on the set of distribution, which is left invariant by this functional. Okay, so probabilists in this situation will think, well, I could try to use a Markovian approach to tackle this problem. So natural question is, I can use perhaps the framework of Harris-Agodic Markov chain. My state space is the state space of point processes, and I will try to work out all the details. And the advantage is that it will give you the existence, uniqueness of equilibrium, and also the convergence to equilibrium, provided that you have everything right. And this is exactly what we want. Okay? So this is, I guess, the way it has been tackled in the past. Okay, so what you have to do, essentially, I do not enter into detail. You have to work out that what is a good reference measure, which is related to the irreducibility condition, and you have to kind of find a kind of Lyapunov inequality, which will tell you if you are in a bad state, large, then if you are patient, after a while, you will return to a nice set of states, smaller. And then if these two conditions are satisfied, then you may expect, with some work, to prove that you have indeed Harris-Agodic. So this is the way. So I will try to develop this Lyapunov style. So assume that you have a bad state, but the bad state is that you have a large number of particles everywhere. So it's, of course, a caricature here. And this is a congested state. Of course, my state space is 0T. And I try to see how I can leave this state. So in this case, this is easy, because if I am looking at the number, when the particle arrives, next particle, then if it's a plus, I will have 1 with probability p plus. And, oh, I'm sorry, there should not be a lambda here. It's a mistake. So there will be p plus if it's a plus, and if I kill somebody, I will subtract 1. But in this, with this state space, with this initial state, I will kill somebody with probability 1, almost. So I will have that, and I will have this simple inequality that if I look at the, so sorry for the lambda, it's wrong, then the rate will be negative under my condition. Okay, so this is, of course, a very comfortable situation. And this one is more interesting. So you assume that it's empty everywhere, except that you have a local congestion. So this is also a bad state. And how you get rid of that? So I have something of width epsilon. Okay? So if I do the same thing, so, and I look at where my minus will be effective. My minus will be effective in the domain of size 2 plus epsilon. Okay? Otherwise, I use this. Okay? Because I tell you that it's empty. And if you try to do that, then you will have only, so the plus is efficient only with this probability. So if your t is sufficiently large, epsilon not large, then it will not be negative. So you will not be able to have some drift condition. And here it's where, when you have a mobile network, you have a local condition. Mobility will just spread all the condition on the whole state space, and this is why it will be stable. But here we don't have that. When we have a local condition, it stays there, and so you have to get rid of that. So I do not say that the Lyapunov function is impossible, but in this case it's difficult to. This is one of the problems that you have if you try to attack this problem like that. Nevertheless, I recently came aware of the work by Lesker and Unger. They had the Lyapunov function for the one-dimensional circle, as you can see. I should not have a precise one-dimensional, perhaps. And they used something that Bruce may like. It was a quadratic function of the point process. But this is very specific, and it's difficult to see how it could work in a more general setting. Okay. So just to say that I will not use Markovian approach to study this problem. I will just use something simple, but there is a simple multiplicity property, and I will use also extensively symmetry in proof. And we'll get what we get when you are Markovian, and you have existence uniqueness and convergence to equilibrium. So we'll fulfill the program without resorting to Markov chain approach. So this is the program. Equilibrium. So I need to introduce what monotonicity, but monotonicity is quite simple. You say that two-point processes are n0 is smaller than n0 if you have that for every subset of I should say every Borelian, but we don't care. We have point processes here. And in other words, just say that the points of n0 are points of n0. And this is another relation. So say that's absolutely continuous. Okay. And there is a proposition. Simple proposition tells you that if your initial state is such that n0 is less than n0, and if you construct nn starting from n0 and mn starting from n0, then you can find a coupling such that this relation holds for at any time. As you can see, this is a very useful function. And it's not difficult because so I will not detail all the cases just to prove that, but it's very simple, just elementary. If N0 are only red and the M0 are only red and purple, then of course only when there is a departure it's important. So when I have a departure and if it kills a purple, no problem, because N0 will be still below because purple was not belonging to that, and even it can be better because it can kill a red, which in CERN becomes a purple. So you have to just to discuss so this is for the greedy algorithm. For the random algorithm, you have to be more careful how you choose your random variable, but this is essentially elementary to prove. Okay, so now I will use something which is more convenient just for notational purpose. Just I will use a shift just to say that I have an operation which drives me from a particle to another. Shift, so just say that the shift of the sequence xn in is xn n plus 1. Okay, and of course, just because the sequence is stationary, my priority is invariant with respect to its shift. It's just to ease the notation. There is nothing under that.
How do you define your shift?
The shift is just simply, you have a stationary sequence. So giving a stationary sequence is just the same thing as the priority space with a shift.
So your stationary sequence, you consider the input flows? And
yes, exactly. Yeah, you have the arrival process. I didn't mention that the arrival process, in fact, your shift is related to the arrival process. Okay. So if I come back to my invariant distribution equation, I want to have a distribution of the point processes so that this holds. Then it will be the same thing if I can find a random variable in M of H which satisfies this equation. Okay? Because n with the shift theta has the same distribution as n. So distribution of n will be the solution of my problem. Okay, that's simple. But it will allow me to work with random variables instead of working with distribution. That's all. That's the reason why it's more convenient. Okay, so this is the equation I want to solve. So what you do is just a simple iterating scheme. You start at 0 and you just iterate your process in the following way. You define n and your shift, of course, is a bijection of your state space, so you don't have to worry about the definition of by induction. And so you have a sequence of n, and it's not difficult to see that, in fact, my n bar n has the same distribution as my initial n sub n, which was starting from 0 and so on. Okay, so I will work with the sequence of random variables now, which are defined like that. Okay, and my previous proposition tells me that, in fact, my random variables are non-decreasing with respect to the order on this probability state space. So I can define that. Okay, and the problem is I don't know if it's a finite process. So all the work I have to do is just to try to find a way of proving that this is indeed a finite point process, and this is all where the work has to be done. Okay? So this is the argument I used a long time ago with this bin packing problem, just using this modesty argument on point processes. Okay, just a few words on the coupling. I don't want to be so the use of shift forever process is in a very nice paper by real Narduski, very difficult to pronounce, but very nice paper to read. And of course, backward coupling is famous paper by Lawrence 62. Another used it by combining with Varelic theory, and it has been quite fashionable for some time that a method called coupling from the past had some success in some community for a long time. And in fact, it turns out that only backward coupling as devised by Lloyd, so it's a proposition. And there is a chapter on the book of Levin and Perez, Wilder, where it's quite well explained. So this is all this part of the literature. Okay, so I'm interested in the analysis of this limit now. Okay, so I will this equation start. Of course, I would like to pass to the limit in this expression. Okay, so there is no problem except here. I do not know what's going on here. What does it mean? And so you see that just because it's increasing, I can only add points. So I may have accumulation points for my point process. So I have to worry about how I should define this variable on a larger state space. So a larger state space should be n star of h, where I can allow some accumulation points. I cannot allow everything, as you will see. And also, at the same time, I will have to extend this functional to this state space. Okay, and once this is done properly, then everything is easy, I would say. So my state space is quite simple. I just consider the set of measures, positive measures, carried by points, such that you have a closed set with empty interior, such that your measure is radon, I will recall the definition, on the complementary of Sm in the space H. That is, for any compact set of this subset, then my measure is finite. Okay? So in that, it's just I remove all the accumulation points, and I impose that out on this set, my measure is radon. This is what I want. Okay. Of course, in our case, the S of M will be the set of accumulation points. So you have an additional condition which is empty interior, just to have a proper definition. And you have to extend this functional, so you add the symmetry state, DAG, and of course, Dirac at DAG is the null measure, Z, and you have to define Tx of M. So in the case when I don't care about the accumulation point, so X has not to be an accumulation point, but I want to consider the case where you have infinitely many points in the neighborhood. This is where you have to define it. So as you will see, this is, and all of that just to pass to the limit in the equation I have. Okay, and of course it depends on the policy. So I will give you 2 examples, I guess, and there are several cases to consider. It's a little annoying by some point, but it depends on several things: the policy and the way the points are accumulated. Okay, so you assume that I'm in a situation where the accumulation point is just at the intersection of these 2 half lines here. And in this case, in fact, this accumulation point, I will remove it from my state space. I define this value as 0. I don't kill any particle in this situation. Okay? And it's easy to understand because just your accumulation, if you kill one particle just because of the number, you don't kill anybody because the accumulation point here will not be part of the state space. So you don't kill a particle. So both for greedy and random. Another situation is when I have an accumulation point around here. So in this case, I define DAG for random policy because I will not kill for the same reason. But greedy, as you can see, I will kill a point for greedy. Okay, so it's natural. All of that, all of this is quite natural to define. Okay, so I would say that we have everything we want. Now you just have to write down an equation. And so there is something which is nice. Just random policy is easier than the greedy policy. It's just I don't have to make any assumption on the state space. So for any state space, if p is less than half, then my point process n has a finite mass almost surely, and it satisfies this equation, which is exactly what I wanted. So random policy is not a problem at all. In some sense, it's more regular. And so the proof I just gave an equation. So it just use a mixture of multiplicities, of relations, and 0-1 arguments.
You have these accumulation points, and if your negative point come near this accumulation point, then it is almost surely nothing happened because
Yes.
it put this positive customer from this accumulation point, and you in this situation, if you have only accumulation points, they will be stable, for example. So the number of customers will not decrease.
I don't know, in this case, no. Because if I have an accumulation point, this is a bad state. This is a bad, I remove it, but it will mean that I will have an infinite number of pluses in my neighborhood. And I don't allow that. When I say that I say that the result is that there is no accumulation point here. This is what it says.
Yes, if
Just to prove that, I have to allow.
But why you said that this random policy is easier? Because it's not good if you have accumulation point. Because after that, if you have accumulation point, then your customer will never come away from this accumulation point because you have infinite number of customers and you cannot isolate this accumulation point from good configuration.
Okay, so but for the random policy, the question does not it doesn't happen. I mean. Okay. Okay, so record greedy policy. So I have to make assumptions on the state space here. For the greedy policy, where you choose the closest plus to kill. And I will assume that a compact structure of a group. So in fact, I will tell about at the end of the generalization, just for convenience. So torus, so circle of dimension d, and a sphere of dimension d, group of matrices, whatever you like, all of this. And you assume that your distribution is invariant with respect to the operation of the group, so it will be for the interest of the examples of interest for us, Lebesgue measure, okay? And so the result we have is just that in this case, then n is also a finite mass, almost surely, and it satisfies this equation. So, and the proof is just almost the same, except that here the symmetry plays a special role, just because everything is homogeneous, and in fact the proof is quite simple. If you think about it, just a simple proof, even simpler than the random case. Okay, so you have this this result that answers Sergei's conjecture in his paper, and a further result is just the convergence, and this is where I need independence of my locations and the signs of my particles. So in this case, I need independence. I should have added, in fact, here. So, but if you have independence, then you have convergence. So the program to show that you have existence and uniqueness and you have a convergence distribution is fulfilled in this case. Okay? So this is a symmetric case. So I will just mention non-symmetrical case, simple one. The interval 0, 1. Okay? 0 t, sorry. So you can define same thing, n like that, and ask that. And the result, in fact, is the same, but it's also a finite mass. And the proof, I just want to show you the proof, because I'm cheating a little here. So I consider S of n the set of accumulation points of n. And so if you assume that S of n is not empty, then it's not difficult, although it requires some work because you have to classify the accumulation points, but that's not the big deal. But the both ends are also accumulation points, because at both ends it's more difficult to kill particles than in the middle, if I may say so. Okay? But in this case, so I have accumulation points here. It means that if I stick together 0 and t, I have distribution which is also invariant with my previous transformation, because here the fact that since there are infinitely many points at 0, which is the same as t, there is, it is the same dynamic on the interval and on the circle. Okay, so just meaning that I have the same distribution as in circle, so n is a finite mass, so consequently the set of accumulation points is necessarily empty. Okay. Okay, so I will come back to this non-symmetrical state space a little later. Okay, so just if we look at that now, we just have used very simple argument: modicity, 0, 1 nodes, symmetry, and inequalities and some complex, and that's all. Nothing very technical, in fact. Okay, you may wonder, and for all cases, we came up with a finite mass at equilibrium. Okay. And you may say, well, why did I need this annoying extension just to prove that it's not there? Okay, so I want to finish by another policy to illustrate in some way this aspect. So this is what I will call local northeast policy. You will see. I guess you have already So local northeast policy is just the same as before, except that okay, when you have a minus, of course it's you have still a small neighborhood, but you kill only in the northeast quadrant. Okay, and you kill the closest one. So this is what's called northeast policy, local northeast policy. Okay, so in this case I kill this guy, and same thing. And I'm assuming, of course, that I'm in a two-dimensional space. My x1 is uniform on H, and this policy, strange policy. And this is a policy which was used in beam technique problem, by the way. Okay, and but you can do the same thing as before. That is, you prove that you have convergence to n, that n is set of accumulation points is also a finite interior almost surely, and so on, so it's in n star of H, and that it satisfies this equation, no problem. And if you take any subset of this part of the state space, then it's finite almost surely. Okay? But the difference here is if you take a point on the boundary, the lower boundary, then it's almost surely an accumulation point. Okay, so you can take any point of the boundary, it will be an accumulation point. There is no way to escape from that. Okay, so drawing, it will be like that. So all the accumulation points will be on this boundary in the two-dimensional case.
So this is not a torus.
I didn't say it was a torus.
No, I just said just to make sure.
You're beginning to be obsessed by the torus, yeah? No. Oh,
Sorry. You have accumulation points in the sense that you have infinitely many particles in the boundary. But why near the boundary you have the larger and larger density of
okay, so I come to this point here. Okay? But this is what happens, in fact. This is a quite surprising phenomenon. And so the proof is just by using some scaling properties with respect to Lebesgue measure. Lebesgue measure has some nice scaling properties, and this is how it is used. I don't go into the detail. I will discuss more the phenomenon. This is indeed a non-trivial phenomenon because you have much more minus than plus, but still the process is building up accumulation points, and you know that every plus is killed with priority 1. Still, in the limit, you have an infinite number of points accumulated. And you can be more precise, in fact. With some, you can make some estimation, and you can show that it is growing at least at rate log of n. Okay, so this is a simple, and I suspect this is not much bigger than that, but I don't know how to prove it. Okay, I suspect this is correct. And if you look at the one-dimensional case, at equilibrium, that is with my infinite number of points, then if a plus at x has an expected lifetime, which is inversely proportional to its position. So it's finite, you are killed with, after an integrable amount of time, but it's related to its location, it's 1 over x. And alpha is some constant, I will come back on that.
So your points are random and they periodically
They're killed.
away,
Yeah.
but nevertheless the total
Yes,
number
it remains stable like that. Okay. Okay, and if you are, so since I have an infinite number of points, I can write them as a sequence, and I can consider this. I renormalize. So I send the points at 0 at infinity back. So log of the vector is just the vector of the log. So I have, in this case, I have points in the upper quadrant of the 0 RD. And if you look at this sequence of points, in fact, and this is a stationary point process on the d-dimensional state space, meaning that if you translate by positive numbers, then you will see the same thing. Okay? And so this is a description how your points accumulate near the boundary. It describes that, the fact that it's a stationary point process. And for something I don't know how to calculate, so you have a stationary point process, its intensity measure is a Lebesgue, proportional to something, which is the rate, but I don't know how to calculate the rate alpha. So alpha is this one. This is the rate of my point process. Okay? So this is a quite interesting example of something which is not completely intuitive. And because you must remember that even if my x1 has values on discrete values, even values converging to 0, I will not have this phenomenon. So,
but in this situation, if you consider arbitrary topological space, maybe it's possible to construct something like that for usual for the topology which you considered at the beginning when you had balls.
Okay, I come back to that later. The list of programs. Okay, so it shows that the fact that I extend from m of h to m star of h is not completely unreasonable. Just if you consider that have some other policies, then you have that. So accumulation points may indeed occur, even in this case. Okay? And also, it's also something that when you start this problem, you have some simple ideas to show how the number of pluses can be just bounded. You can have very nice ideas. But if you remember that for this example it doesn't work, then you will see that several of them are wrong. And it's not so easy, even myself. I was trapped several times when I work on this problem, but I had that in mind. So fortunately I did. So this is also something which is useful. But the argument we will use for greedy or random, you should test them in this case. And if they work in this case, you are on the bad way. Okay? So this is the benefit of this negative result. It's not a negative result, it's a nice result, but okay. Further question, without symmetry, so this is what maybe Sasha was mentioning for greedy. So when you remove symmetry, I guess, provided that you have some regularity, meaning that you have Lebesgue density, then with some regularity condition, you may have this result. Or I should not have said RD, it's a compact subset of RD, of course, in this case. Invariant distribution, these, as far as I checked, it doesn't seem to be Poisson. So, and I almost know only Poisson distribution. So I have not been able to have any idea of what we can say about invariant distribution in this setting. Uniqueness, so this is a more theoretical result. Here what I prove is that if you start from a finite number of points, you converge to unique. I didn't study the fact that I could start with an accumulation point, so this is maybe one of the questions, and where do I end? So I know several examples, like the circle, where if I start with a point process with accumulation point, then I will converge to my finite process with a reasonable assumption. So there is uniqueness in this state, but in general I don't know. And it's not very far from, as in a Garcia-Kurtz setting, that when you have a non-compact state space, then you replace your location by a Poisson process of this product space, and you may wonder, is there existence? So existence, using the result I mentioned, can be proved, yes. Uniqueness is, I suppose that it's yes, but I don't know how to prove it. It's a little more complicated, I guess. Okay. Conclusion. I think this is an interesting set of problems that they are wrong, and quite promising, just because there are some questions which are not common in our community, and the idea was to study other Barthes processes. So I mentioned several works in this domain, so you have several ways of interaction. So it could be interesting to have a set of classes of Barthes processes that one could study. And also how one can handle long-term behavior of these processes without too much details, technical details. Because if you may jump into, so I was mentioning Harris Markov chain, but you would like to use as few as simplest possible argument. So this is one of the questions I have. And okay, the paper is in the archive, and that's it.
Very much. Questions, comments?
Is it known something if lambda plus is much smaller than?
What can you expect?
You have
It's kind of mixing property, independence of the invariant distribution.
well, you have fixed space, topological space, and then you have an extra restriction. For example, lambda plus is you have some inequality, as it will be the small perturbation.
Yes. So this is what thinking of independence relation for the invariant distribution.
Empties.
No.
Empty. If it will be the small perturbation
Yes.
of empty situation.
The perturbation of the empty system can be anything. Just
it is not.
we don't have an independent model in the limit. This is the trouble I see here. But I have no idea of that. Because no, for your lambda plus small, I see maybe some for the invariant distribution. We may say something in this case, perhaps, just as because interaction is not that it's not that important in this case.
In this situation, you have usually nothing when you come with a negative particle. You have nothing or one positive particle in the middle.
Yeah, you will have basically an empty system. Yeah.
Maybe it is.
Maybe it will be interesting by growing also the state space at the same time, just by looking at the scaling. Lambda goes to infinity, but considering a larger state space. Yes.
What happens if you remove 2 points?
Hmm?
What happens to your equation if you remove 2 points?
If I remove 2 points, I guess most you can do most of things because the main properties are preserved.
Same.
Yes, yes. I don't think it makes a difference.
So any finite number of points would not change.
Yeah, it will not.
Qualitative.
No, it will not change. No, it will not change just because. Yeah, no, there is no problem with that.
So the way to change the quality behavior is to remove all the points.
No, there is another problem by Sergei where you consider greedy server. You have only one server traveling along, and this is this doesn't work.
If you remove, so if you remove,
Yes. Yes, but because you have to keep track of the location of the server, and this is and here you cannot use. Otherwise, I would have handled that.
if you,
Stephen, is Tom Kurtz here?
Yes, he's
Where is he?
I can't hear back
Oh,
here.
sorry, Tom. Is this at all related to the things that you've been doing with Alison and Amandine and the Beresticki brothers and stuff? It has that same flavour, right? Of points sort of arriving and having sort of areas of influence and.
he has a paper with Garcia.
No. This is not that. This is.
Oh.
I mean, Alison's model has this sort of flavour, right? In some sense.
Yeah,
but-
you're right. That's a good point.
Well, yeah.
What is
Yeah, I mean,
Allison?
Sorry to put you on the spot, but it's just that you're.
In her model, there are sort of mass killing events. That's I think that's the big difference is that
You kill everybody?
the circle comes down and with some probability, depending on individuals that are in that circle are killed independently with some probability, and then you drop another circle and then individuals get born and so on. Yeah. So, but you're right, there is a connection.
You come.
If you kill the most distant in the circle, would you perhaps get?
I don't have any comparison results when what I can say is but that's quite easy. You have less points in the end, so you can order your equilibrium with the size of your neighborhood. But other than that, I cannot say much more. I would say.
Yeah, I think that insisting in the discrete case, you probably can construct a non-trivial model if you are allowed to kill people that is far away, because in that way you will have some dependency. Because in order to kill, if you arrive here, in order to kill your neighbor, you must be empty here, right?
Yes.
So you create some dependency
I doubt it.
between these cubes.
I really doubt it because it's really something which is related with Lebesgue measure, and I doubt it really because. I didn't say that. Just the way it's accumulating. It just, I guess, it's a sequence of rare events that occur.
No, but I am not talking about this model, about the other one, the first one.
Yeah, I'm sorry.
No, this one I don't think that you can get something in the discrete.
Yeah.
But in the other, in the local one, with no orientation.
Yes, but you don't have any problem here. You don't have accumulation points and whatsoever.
No.
Any further questions? If not, first of all, before thanking the speaker, I was asked to tell you, please look at the information on the two screens. And now let us thank Phillippe once more and then go to lunch.